Okay, today I'm going to give you two things. The first one is going to be use of op amps in mechatronic or control applications. Now, we've talked quite a bit about op amps in the past, and one of the reasons I kind of want to give you this presentation is because it turns out they're still very useful for relatively simple control problems, and for very little money, you can accurately control something. In fact, many times you can control it more accurately than you can with a digital implementation. So this is just a control application of mechatronics, and I show in this a dotted line around here, and these are the things that you could implement using the op amp. We've got the controller, we have the summing junction. This is very similar to what we did in 5310 when we were controlling the voltage out of the generator. And so I show in this a power amp, and then this is a motor model, or any first order, any system that can be modeled as a first order system. And so typically, if there's a motor, the op amps can produce about 20 milliamps on a good day, and after that they current limit, and they do this by folding back. It's a very interesting waveform. If I had a sine wave that was current limiting, it actually folds the current back and will put cups on top of the sine wave like that. It's I was looking at doing this for a controller on an airplane one time, and we were having some current limit issues, and it was folding like that, and the supervisor for the group I was doing the consulting for said, "Why does it do that?" And I said, "Well, I'm not doing it." I said, "On my best day, I don't think I could make a circuit that did that." And so, but this is due to the current limit on the amp. So if you ever see that in a circuit, that cupping shape is usually due to something that's current limiting. And anyway, that's a little bit of an aside. So if I only have 20 milliamps out of an op amp, I've got to put a power amp in this, and all this does is it can literally have a voltage gain of 1, but it's capable of providing more power, and we've talked a little bit about that before. So I can do a summing junction. I can build a summing junction with op amps. This is a differencing amplifier, and you'll notice that all of the resistors are the same. And so in that case, what this gives me is, if I were measuring a velocity of a tachometer, and I had some rotational velocity I wanted to set on the motor shaft, I would build this, and this is the transfer function of the system, so if I divided that out, it would be, so basically it implements this in electronics. And so and since I've got all the resistors equal, there's no gain, so that's a 1, and so it literally just subtracts the two voltages. Sometimes when you're building systems with op amps, you've got inverting and non-inverting configurations, and you won't have the right number of signs, and so sometimes you may have to swap these and actually subtract the one that you think should be positive from the other, but that's just counting signs as you're going through your system. So sometimes you need a negative sign, and you can do that. Second thing is a summing amplifier, in which case this is, I would have to put in a negative voltage here, and then I still get the sum out of this, and because of its inverting, I get the negative sign there. And so basically this is just sign accounting, and so I just have to make sure that everything that I do, I account for all the signs as I'm going through the system. If I miss a sign, I'm going to end up with the positive feedback, which is one of those experiences that you need to have when a system goes full unstable due to positive feedback. Okay, for the controller, if I did just a proportional controller, then I could do this with a non-inverting configuration. So I can build this. This is just K proportional in that case. And in that case, I've got an error voltage times gain. The one thing you will notice is that this gain can never be less than 1 or even equal to 1. Well, it can if you float R1 to infinity, but which you do in a buffer. Or it can be inverting. Inverting amplifiers can actually attenuate also. So in this case, I could have R2 less than R1, and I could actually build an attenuator instead of something with gain. So it would multiply the V error in the input by some number less than 1 and produce a smaller voltage on the output. It has uses. Okay, for integral control, if I want to add this, so just kind of marching through a PID controller, I can put in an integrator. And so I've got some questions here. They're good for you to kind of read through. Can I get zero steady state error with proportional control? For this system, I can't because I don't have a free integrator in it. And so adding the integrator would allow me to zero the steady state error. I want you to think about this physically. A lot of times we get wrapped up in the diagrams and mathematics and we don't think about what's going on in a physical sense. What is this physical device doing? And it's better to do that. And so if I were to allow steady state error to go to 0 in my original system, if my error went to 0, then if I were just had a proportional, I was multiplying it, that means this voltage would go to 0. And that in turn means that this voltage would go to 0 and the motor would stop turning. And that doesn't make any sense. And so this error can never go to 0. It's just a proportional gain. Adding the integrator allows me to take care of that problem. Okay, so I can build an integrator simply out of an op-amp. Resistor, capacitor, I do the formula. Go back to op-amps are easy if this is mystifying you. And I get that. What this has is some scale factor and a 1 over S. And it's got a negative sign since an inverting configuration. Something, again, I'll have to take into account while I'm building the system. Okay, so this thing moves. This thing will drift. It drifts because there's a very small bias current that's flowing into the op-amp, and that causes this to crawl around, and so this will tend to go to a rail. So if I build one of these in the lab, they will tend to go up to a rail and stay there, or they can go down to a rail and stay there. Now, modern op-amps are pretty good, and so if you do this with a 741, it will rail before you can watch it rail. And so, but with like the TLO82, yes, it is my favorite op-amp, 82 or 84, or there's also 72 or 74, these op-amps, you can actually turn them on and watch it move. It'll take a few seconds to get up there. Now, why would I use one of these if it drifts? Well, because I can zero the steady state error. I mean, that's really good. Now you'll see people say, let's put a resistor around there. This is bad. Okay, yeah, it stabilizes the amp, but it turns it into a low pass filter. It moves the pole from being on the origin into the left half plane, but it doesn't give you what you want. Then it's just a filter. It's just a low pass filter. And so this is a bad idea. Okay. So if I really want to use this, I put it in the circuit. And if I put it in a negative feedback system, the system itself will take care of any drift that this device creates. And so I don't have to worry about it if it's in feedback. So when I use these in feedback, they're pretty trouble-free. And like I say, with a modern op-amp, drift is so slow, it's not going to substantially affect my steady state error, and I'll still be able to zero steady state error, which is really a good thing when I'm building systems. Okay, derivative control. If I wanted to add a derivative control to do a full PID, I can add derivative control. One of the primary reasons I add derivative control is it's anticipatory. The large changes in slope. So if it sees a large change in slope on its input, then it produces a an output that's proportional in some way to that change in slope. And so it sees big changes and it can then try to fix them, or it can then try to track them. And so on the first cut, I would want ZF over ZI to be some proportionality times S. And so I can do this one. I can make a derivative that is just the sort of, I can reverse the positions of the R and the C from the integrator. And lo and behold, it does produce exactly what I wanted up here. But it's troublesome. The major reason this is troublesome is that if I look at the Bode plot for an integrator, it goes down to the minus 20 dB slope. As omega gets bigger and bigger, the value gets smaller and smaller. Whereas a differentiator, it goes up with a 20 dB per decade slope. And so as I get higher and higher frequency, it's taking any noise in its input signal that occurs and amplifying it, making it bigger. So this circuit will tend to take input noise and make it bigger, and that's not good. Okay, so in general, I'm not going to want to use that direct derivative, and I show that here. But as a better circuit, I can put another capacitor in this circuit around this device, and what I get is I still get an integrator, but then I knock the integrator down. So the Bode plot of this system will look like this. The integrator or differentiator will look like this. Then I get to where that pole is, and I just flatten out. Still problematic because this region here is still amplifying the frequency components, high frequency components that come on its input. Because if this were 0 dB, showing the 0 dB crossing there. And so that's not good either. And so I don't really want to amplify those. I prefer not to have really, really super noisy systems. So it's not perfect, it's better. Now, one more differentiator. I can do this. And I can add an additional resistor in series with the capacitor. And when I do this one, there it is. There's the differentiator part. And I get two poles now. Okay, and so I arrange these poles so I get a Bode plot that looks like this. And so in this region, it's a differentiator. And then it gets knocked down, then it gets knocked down again, and it goes to 0. So I show this as omega goes to infinity, that both capacitors short. And so what I get in that case is it's down here, and the low frequency is equivalent to this, the low frequency transfer function, and so I get what I need. I don't amplify high frequency noise, and I still get the derivative action where I need it. And so this is just so you'll know, differentiation in general is a really, really bad idea unless you do something like this. If I take a signal and try to take its derivative, I will amplify any high frequency noise that occurs in it. And so if I end up looking at a system and saying, well, in order to get the signal I want or the information I want, I need to take its derivative, be really careful with that. There are ways to do this for sequences. If I have a digital sequence of data, then I can, if I have the whole sequence, I can filter it digitally forward and then filter the sequence digitally backwards, eliminate all phase shift, and I can actually take a derivative without too much problem, but you have to have the entire sequence, which means this is useless for control. So that's one thing. So if I add these controllers together, I can do my proportional I can do my integral, and I can do my derivative controller. I can make one of these resistors variable or do something like that. I can sum them all together and produce a PID controller. Okay. So that said, I believe I mentioned this before, but there's another cool thing you can do with op amps is a voltage to current converter using a transistor to get a little extra current, and a sense resistor. And this is a really simple analysis here. Shows you that the I through the motor is just equal to the Vn divided by the sense resistor. And if I do this on a brushed DC motor, put constant current through it, I will get constant torque out of the device, and which is kind of fun. Okay, hopefully that helped you understand things a little better, and I'm going to go on and make another one here in a few minutes about state space Kalman filter observers and Kalman filter observers. So I'll do that